In this video, I will be showing you how to do integration by U-Substitution, a process which is much like the chain rule for taking a derivative. And it's what you need to do whenever your antiderivatives have another thing within the inside other than a variable x. So for example, say we had, say for example, we had the integral e to the x squared or something. Now actually, this is an antiderivative we can't solve via U-substitution, but it helps us understand the idea. But it's the process that we can try to use if there's something other than just x within our antiderivative. And the goal is to say, well, if I can change that to u, then I could apply an established integration formula that I know to try to solve the antiderivative. However, one thing about performing U-substitution that's very important before we get into some examples is you need to change the entire antiderivative to u. Both the inside and the differential. Because if I was to just say, for example, I had this particular antiderivative, the antiderivative of e to the x squared with respect to x, and I was to just change x squared to u and leave dx as it were. Basically, you can't integrate this because there's not a match in the variables. Those things are not matching, which means that if you just apply this particular rule, it's not going to work. So part of the process of U-substitution is changing your interior to u in order to use a proper formula for finding the antiderivative, and then also changing dx to du through some method. And that's what we're going to be focusing on. Sometimes I might refer to this as the reverse chain rule because that's the idea. But like, let's say, for example, we look at an antiderivative. Let's say the antiderivative of x cubed, which by the reverse power rule, we know that that is x to the fourth divided by 4 plus c. Now the question is, well, what if we change the inside instead of just having x cubed? What if we change it to 4x minus 5 quantity cubed? Would that obey the same power rule? Add 1, drop the reciprocal, and would this work? Well, we could quickly check to see if this makes sense by taking the derivative of this, right? And that, you know, as I was, when I was teaching you guys antiderivatives, one of the most important things to remember when you're taking an antiderivative is to check yourself. If I take the derivative of my answer, does it return back to where I started? And in this particular case, well, the 1/4 won't affect the derivative, so we could factor that coefficient out first. And then in order to differentiate 4x minus 5 to the 4th power, I could multiply all that out, but it would be much easier just to use the chain rule. Which, remember, the chain rule says, well, I take the derivative of the exterior function, so I could apply the power rule, drop the 4, keep the inside the same, and subtract 1. And then by the chain rule, I have to multiply by the derivative of the inside to compensate. So again, just to reiterate, the chain rule is derivative of the exterior, which is the function to the 4th power, leave the inside alone, and then multiply by the derivative of the inside. And all in all, this would give us 4 times 4x minus 5 quantity cubed as our derivative. And so to answer this original question, did this make sense? Did changing x cubed in this antiderivative to 4x minus 5 cubed make it so that the same exact power rule, reverse power rule, will still work? And the short answer is no. Notice that this is not the correct answer, because what we should have is an additional factor of 4. And the question is, well, how do I deal with such a thing? And the short answer is we can use U-substitution in order to do that. So let's go ahead and look at how we would do this using U-substitution. But like I was saying at the beginning of the video, the primary goal is to change the interior to u. So basically I would have 4x minus 5, that whole thing I would just change to u cubed. Now this is a much simpler antiderivative. I could use the power rule on this because it is in the proper state. It is just the variable by itself to the 3rd power. But the issue that is, again, as I was saying earlier, is that dx will not be a match. So the question is, well, if I'm trying to take the antiderivative of this is not going to work because they're not matching in their variables. So naturally what we want to do is change dx to terms of du as well. And the next question is, well, how do I do that? But it's quite simple if you just write out the algebraic statement of the substitution. So what we did is we took 4x minus 5 and we set that equal to u. Or, you know, the simple strategy here, it says let u being what is in the interior. And then it says to find du by differentiating both sides with respect to x. Well, remember that a differential du, if I wanted to know what is du dx, that would just mean the derivative. So if I could take the derivative of both sides like this, and what I would have is, well, the derivative of 4x is 4, and the derivative of any constant is always 0. And usually, instead of writing it like this, remember a few weeks ago, or maybe about a month ago, when we talked about differentials, technically I can multiply across both sides by dx, and that's usually what I would do instead. Instead of writing du dx, which means the same thing, I would just write, well, the derivative of u is equal to 4 dx times, and just differentiate with respect to x and leaving the dx on the other side. Or what you could kind of remember is if you have u is equal to something, du will be equal to the derivative of that something times dx. So more simplistically speaking, it's just, du dx. Usually we just write the dx on the other side so that we are ready to go. And so again, well, where do I go from here? Well, last but not least, the goal was, sort of looking at this antiderivative. I changed this into u cubed. And then the kind of the other question is, well, how do I change dx into du? But this is an algebraic statement. You can actually solve for dx. So after you set u, take the derivative, I could divide both sides by 4 here to actually figure out, well, du divided by 4 is equal to dx. And I could just make that substitution. So basically, dx, I've now solved what that amounts to in terms of du. So it's like I changed my integrand, which is the portion in between the integral symbol and the dx, I changed that to terms of u. And after I try to figure out, well, how do I change dx to du? And that's always done by taking the derivative. And then algebra. And basically from here, now at this point in the semester, we've never probably looked at an example where we've written anything attached to the dx. It's usually just something which I was like, don't worry about that. That's at the end of the integral. But it is an algebraic state, like it's part of, like you could think about it algebraically as well. So like in this case, du over 4, that's just like a 1/4, and you could write that in a number of ways. You could write this as 1/4 u cubed du. Let me fix that a little bit. Or I could even write the 1/4 through here. So again, this is all work you wouldn't need to do, but just in terms of, if you're wondering, how does the algebra work when I'm writing something in terms of this way? But it's just like if I have a 1/4 on the inside of my integral or on the du or in front, they're all equivalent. It's just a flat coefficient at the end of the day. And how I'd probably write it would just be, well, that's a 1/4, that's equivalent to meaning 1/4 times the u. And so I'll just write that 1/4 out front instead. And from here, now I am ready to solve this antiderivative because everything is in terms of u. And the antiderivative of u cubed with respect to u is u to the 4th over 4. And of course, I would need plus c because I'm taking a indefinite integral. And in a couple videos, I'll show you how you can solve definite integrals via U-substitution as well. It's very similar. If U-substitution is something that's a little bit new or different for you, something that you might remember from algebra, where if you have an equation, say something like this, and we want to know, well, how do I factor it? One strategy for solving what are called quadratic forms is by taking the middle term and setting that to be u. And if u is x squared, then x to the 4th would be u squared. And it's sort of like I can take a polynomial that I'm not really used to dealing with and change it using a u substitution as a way of recognizing, okay, this is a quadratic, I could factor this as I would normally factor something. It's sort of the same, it is the same strategy for integration. You just have to be careful with your dx when you're doing the substitution. And also, I'm not quite done yet because the last step is, just like with any substitution, my original goal was to solve the antiderivative of this function with respect to x. Now, writing an answer in terms of u is not very good because I've changed it all around. So the last step after solving the integral is to actually reverse a substitution or plug back in u at the end. I should have put that as another step here. But basically, u is equal to 4x minus 5. Now that I've solved the antiderivative, well, I have 1/4 times 1/4 is 1/16. So I just have u to the 4th, and u is 4x minus 5, as I wrote. And then that's all going to be over 4 times 4, which is 16. So my final antiderivative here will be 4x minus 5 to the fourth divided by 16 plus c. And also going back to this original issue here where this didn't, we came up with the wrong answer. Notice that our answer, we thought, or we didn't think, but we hypothesized that if it worked the same as this one, we would just add 1 and drop the reciprocal. But notice that the correct answer actually has an additional factor of division by 4. Because notice, because of the chain rule, this is why we call it the reverse chain rule. When I did the chain rule on this derivative, I got an additional 4 that popped out from that chain rule. So notice that when I'm doing the U-substitution, I get an additional 1/4, the reciprocal, because an antiderivative is the opposite of derivative. So when I'm like sort of trying to undo the chain rule in this way, I actually get the reverse factor in here. And U-substitution is cool because it doesn't have to just be used for the chain rule. It can be used for a lot of different types of integrals. And the last thing I wanted to mention before we move into more examples is U-substitution does not always work. You cannot solve any integral using it. Only very specific ones will work. So there are other strategies you need, and there are certain types of integrals that actually have no algebraic solution. They're basically, you cannot solve them using simplistic mathematical functions. And that's something, we're not going to really get into how you actually do that, but it's quite an interesting subject in my opinion. Anyways, that'll wrap up this intro to U-substitution. In the next video, I'll do more examples of both definite and indefinite integrals by U-substitution.